The James Webb Telescope may have detected the biosignature of an alien civilization on K2-18B. Specifically, it has found traces of a sulfur compound, dimethyl sulfide (DMS), which is typically produced by organisms on Earth. But how did experts manage to identify potential biomarkers in the atmosphere of this exoplanet? Will we finally be able to answer humanity's oldest question? Are we truly alone in the universe? And if there are extraterrestrials, why aren't they here? This last question is not new. It addresses the heart of the unsettling Fermi paradox, proposed by physicist Enrico Fermi in 1950, which deals with the mysterious absence of extraterrestrial neighbors. In principle, one might think that the universe, with its vastness and countless celestial bodies, would allow the development of innumerable civilizations. And yet, there is still no evidence of other civilizations, at least officially. Of course, countless rumors circulate on the internet, claiming to show strange flying objects that are literally not of this world. Then there are the statements from figures like David Grush or Bob Lazar, who assert that the U.S. government has been running a secret UFO recovery program for decades. But before diving too deeply into these controversial speculations, we should stick to the officially confirmed facts. Despite brilliant records and the wow signals, we still have no concrete evidence that we're not the only intelligent life in the universe. But isn't that strange, given the thousands and thousands of stars in the sky? Could it really be possible that Earth is the only celestial body to have produced intelligent life? Several researchers, including Tom Watsby and Christopher Consolis from the University of Nottingham, have addressed this question with a categorical answer. In a study on astrophysics, they concluded that 36 highly developed civilizations might exist within our own Milky Way. Watsby and Consolis explained that the reason we haven't made contact with them is likely due to the immense distances separating different extraterrestrial civilizations, an average of 17,000 light-years apart. To clarify, 1 light-year is the distance that light travels in a vacuum in 1 year, about 9.46 trillion kilometers. Theoretical astrophysics is fascinating, but is there a more practical way to approach this topic? The answer is yes. As you may know, the James Webb Space Telescope has been shining an infrared light on the deepest secrets of the universe for over 2 years now. It has reminded us once again how much our understanding of the cosmos was limited in the past. As the most powerful space telescope in history, Webb can detect the heat from a bumblebee on the surface of the Moon from Earth. However, the telescope, specially designed for infrared astronomy, is not particularly interested in chubby insects, preferring instead to offer us spectacular images of deep space, such as the James Webb Deep Field or the Pillars of Creation. Yet, since the start of its scientific mission in the summer of 2022, Webb has uncovered a few mysteries. It has discovered a series of galaxies that appear far too massive and developed for their age, a few 100 million years after the Big Bang. These galaxies are in stark contradiction to current cosmological models. Moreover, the data collected by Webb should allow us to delve deeper into the mystery of what we call the Hubble constant. We still don't know why the universe is expanding today faster than our theories predict. What we do know, however, is that there is an exoplanet called K2-18B, which has quite a remarkable feature. Located in the Lyra constellation, about 125 light-years away from Earth, this planet is suspected to harbor an entirely oceanic world. However, planets like K2-18b have a significant problem. Up until now, they only existed on paper, described theoretically as a potentially habitable exoplanet covered in water. In practice, though, the data collected so far suggests that K2-18b could indeed be a humid and hospitable place. In fact, previous telescopes such as Hubble, Kepler, and Spitzer had already collected data before Webb's launch, and these data strongly suggested that the planet's atmosphere contains water vapor. It is well known that the presence of liquid water is a fundamental condition for the emergence of life similar to that on Earth. And since K2-18b is located in the habitable zone of its parent star, this condition seems to be in place. The exoplanet orbits around a cooler, less energetic star called K2-18, at a distance that allows for the presence of liquid water. Specifically, the distance between the two bodies is only about 0.14 astronomical units, meaning K2-18b takes just 33 days to complete one orbit. However, since its star emits much less energy and heat than our Sun, K2-18B receives roughly the same amount of radiation as Earth. In terms of mass, however, the differences are much more pronounced. The exoplanet has 7 to 10 times the mass of Earth and is classified as of super-Earth. But it's important to note that this term refers only to mass, not necessarily the planet's habitability. Could there be alien life on K2-18B? We've known about K2-18B since 2015, but the discovery that its atmosphere contains dimethyl sulfide, DMS, is something we only learned about in recent months. To understand why this discovery could be so revolutionary, let's revisit what we mentioned earlier. On Earth, DMS is primarily produced by living organisms, particularly microscopic organisms like phytoplankton. DMS is a primary source of sulfur in the atmosphere and acts as a cloud seed, providing the typical oceanic smell. The fact that Webb's data, collected with its near-infrared spectrometers, NIRSpec, includes spectral marks of methane, carbon dioxide, and now DMS, has been described by lead researchers
if astronomers
from the
have really
succeeded in detecting
Riverside
DMS,
as the proverbial
dimethyl
cherry on
sulfide, on K2-18B, this could be a strong sign of the existence of extraterrestrial life. But why is it that, despite this promising discovery, scientists are still showing prudence? Well, the reason the existence of extraterrestrial neighbors hasn't been officially announced is because the detected DMS signal was not particularly strong. Furthermore, it was only revealed after specialists reanalyzed the data from the Webb telescope in a very specific way. To put the data to the test once again, the specialists decided to reconstruct the water planet and its possible biochemistry using several models. In these models, they simulated the ocean and atmosphere of the presumed planet and then examined the amount of DMS that organisms would need to produce for it to accumulate in the planet's gas envelope. At the same time, the researchers tested the rate at which DMS decomposes under radiation and in which region of the atmosphere it would be expected to break down. The exciting result of this study is that biogenic sulfur gases can indeed accumulate in detectable concentrations on planets that are rich in hydrogen. However, this would only be conceivable if the organisms on K2-18B were far more industrious than their earthly counterparts, as they would need to produce 20 times more DMS than Earth's organisms. The reason for this is simple. A large portion of DMS decomposes immediately due to standard irradiation, which leads to photochemical decomposition. However, if concentrations are higher, which would not be unusual for an oceanic planet, the decomposition products of DMS can have a protective effect. Molecules such as dimethyl sulfide or methanethiol act like a sort of shield for the lower atmospheric layers and prevent the continued breakdown of DMS. But is it possible, outside of these theoretical models, to get a more direct idea of the actual presence of DMS on K2-18B? Yes, fortunately it is possible, but not with the current Webb telescope. The DMS signal detected by Webb appears at a spectral wavelength of 3.4 microns, which overlaps with the methane signal. To separate the two molecular values more clearly, the researchers will rely on the MIRI, mid-infrared instrument, spectrometer on Webb. This instrument works in the medium infrared range, exactly where DMS and its accompanying products leave their trace. Unless an unexpected issue arises, scientists should be able to crack the mystery of K2-18B's atmosphere by the end of this year. So, we may soon know more about the atmospheric signatures of this distant world. And with that, perhaps we'll learn that we are not alone in the universe. Don't forget to leave your comments below our video and show us that we are not alone in the universe. Like and subscribe so you never miss a new video from us. See you soon.